What do you expect from the smallest planet in the solar system? Probably nothing. It's a scorched rock. No atmosphere, no weather, no volcanoes, and barely any gravity to hold on to anything interesting. But that's the problem. Mercury isn't acting like that. Right now, it's giving off something strange, something we weren't even looking for. New images and data are showing gases leaking from its surface, glowing chemical tails stretching behind it, and now, for the first time, traces of lithium in its exosphere. That's not just unusual. It doesn't make sense. Why is Mercury, of all planets, emitting stuff it shouldn't even have? And how are scientists just now seeing it? Whatever's going on, it's not quiet anymore. For decades, Mercury was treated like the least interesting planet in the solar system. It was small, airless, and scorched by the sun. No atmosphere, no weather, and no sign that it ever had the kind of geological activity that would make it worth studying in detail. The basic idea was simple. Mercury formed, cooled, and became a dead rock. That was the story. Scientists assumed that whatever was going to happen on Mercury already happened billions of years ago. The planet's size played a big role in that assumption. Mercury is the smallest of the 8 planets, with a diameter of only 4,879 kilometers, not much bigger than our Moon. Small planets lose internal heat quickly, so any volcanic or tectonic activity should have ended early in its history. There shouldn't be any fresh material cycling through the crust. No internal heat means no convection, no magma, and no gas release. Everything should have frozen in place a long time ago. Mercury is extremely close to the Sun, only about 1/3 as far as Earth, and for a long time this seemed to confirm what scientists believed. The planet should be dry, stripped, and made almost entirely of heavy materials. Its orbit is the most eccentric and inclined of any major planet, swinging it from 46 to 70 million kilometers from the Sun and producing the largest relativistic effects in the solar system. For more than 60 years, Mercury's orbit was astronomy's biggest puzzle. Its closest point to the Sun kept shifting slightly by 43 arcseconds each century, in a way Newton's laws couldn't explain. Then, in November 1915, Albert Einstein showed that his brand new general theory of relativity accounted for the discrepancy exactly without adjustable parameters. A calculation so perfect that it left him, in his own words, beside myself with joyous excitement, and caused actual heart palpitations. Its rotation added to this picture of an extreme, inhospitable planet. Mercury spins very slowly, taking 58.6 Earth days to complete one rotation. Because of its 3:2 spin-orbit resonance, a full solar day on Mercury, sunrise to sunrise, lasts 176 Earth days. This produces one of the strangest sky motions in the solar system. Around perihelion, the Sun appears to rise, slow down, briefly reverse its path, and then continue forward again. Combined with the planet's slow rotation, this leads to brutal temperature swings from about 430 degrees Celsius on the dayside to minus 180 degrees Celsius at night. And the mysteries don't end at the surface. Mercury formed in a much hotter part of the early solar system, where light elements like sodium and potassium should not have survived. Scientists assumed these materials would have evaporated away or never been collected in the first place. A planet this close to the Sun was expected to be nothing more than heavy metal and rock, iron, nickel, and silicates. And with no real atmosphere, Mercury was expected to be static. An atmosphere can move heat, shape surfaces, and interact with sunlight. Without one, Mercury was expected to sit under the Sun with no real change. Day after day, year after year. All that exposure should have left the surface baked and chemically simple. There was no reason to think anything was being released, emitted, or carried away. It was assumed to be inert. Even when Mariner 10 flew past Mercury in the 1970s, the mission didn't challenge any of these ideas. The photos it returned showed a cratered surface that looked a lot like the Moon. No signs of active processes. No signs of motion. Nothing that hinted Mercury was still doing anything at all. It was easy to believe the old picture. Mercury was just a leftover rock from the early days of the solar system. Interesting historically, maybe, but not active now. These ideas were so widely accepted that they shaped entire models of planetary formation. Mercury became a reference point. If you want to know what a planet looks like after everything has stopped, look at Mercury. If you want to know what happens when a planet is too close to its star to hold onto gases, look at Mercury. If you want to know what a dead planet looks like, look at Mercury. That's why everything happening now is surprising. The discoveries being made today aren't just new details about a familiar place. They're breaking the assumptions that defined it. Scientists didn't expect Mercury to be releasing material. They didn't expect new elements to be detected. They didn't expect anything worth tracking or monitoring in real time. And now we're seeing evidence that the planet is still shedding, reacting, and changing. Despite having the most eccentric orbit of any planet and the second highest density, it stubbornly retains water ice in permanently shadowed polar craters, hundreds of billions to a trillion tons shielded by a dark organic-rich lag layer, and continues to shrink globally as its oversized core cools. This first section matters because it shows how deeply the old model was ingrained. Mercury wasn't ignored because it was boring. It was ignored because scientists believed they already understood it. A planet like that shouldn't have anything left to reveal, but it does. And that's where everything else begins. Mercury doesn't have an atmosphere. That's been clear for a long time, but it does have something thinner, a layer of particles called an exosphere. This isn't a gas blanket like what Earth has. It's a scattered, almost vacuum-like zone where individual atoms bounce around for short periods before falling back down or escaping into space. It's fragile. It's constantly being stripped by sunlight and solar wind. And somehow, it's filled with elements Mercury shouldn't still have. The main one that's drawn attention for years is sodium. Sodium atoms glow under ultraviolet light and can be spotted from Earth-based telescopes. Observers have captured images showing sodium streaming away from Mercury, forming a long, faint tail that follows the planet in its orbit. This tail can stretch tens of thousands of kilometers, and in some observations even millions of kilometers, or hundreds of Mercury radii, as radiation pressure pushes them away from the sun. The tail isn't thick or bright like a comet's, but it's real, measurable, and surprisingly abundant. Then there's potassium. It's less abundant than sodium, but has also been detected in Mercury's exosphere. Recent measurements have shown a potassium tail extending out behind the planet. It doesn't reach as far as sodium's, and it's more difficult to detect, but it's there. These emissions are not temporary events. They appear regularly and suggest ongoing release processes. That's the part that contradicts what many scientists expected. Alongside sodium and potassium, there are also traces of calcium and magnesium. These were detected by the Messenger spacecraft and confirmed across several flybys. Calcium is heavier and tends to stay closer to the surface, but even that is escaping. Magnesium is present too, though at lower concentrations. Messenger also revealed abundant sulfur on the surface, far more than expected, further challenging the idea that extreme heat stripped away all lighter elements. These lighter elements are surprisingly persistent, given Mercury's weak gravity and constant exposure to solar radiation. And now there's lithium. This is the most recent and unusual addition. In 2025, researchers going back through Messenger's ultraviolet spectrometer data noticed faint but consistent signals that match lithium's emission lines. After ruling out noise and contamination, the signal held up. Lithium is now part of the known chemical makeup of Mercury's exosphere. It's not just a theory, it's been measured. And it wasn't expected. The detection of lithium matters because lithium is a volatile element. It doesn't last long under solar radiation. For it to be present now, something has to be replenishing it. Either it's being knocked off the surface by micro-impacts, or it's being released through some surface exosphere interaction that hasn't been fully explained yet. This adds to the list of elements Mercury is leaking into space, despite being thought of as depleted long ago. The methods used to find all this aren't new, but they've become more precise. Most of the current data comes from spectroscopy, breaking down the light Mercury reflects and emits to see what elements are present. Ultraviolet spectrometers on MESSENGER were able to detect faint emission lines corresponding to these atoms. Ground-based observations have helped as well, especially for the sodium tail, which can be imaged directly. But it's not just about the technology, it's about what's showing up in the data. These emissions are steady, not explosive. They're not the result of volcanoes or vents. They're not dramatic, but they're active and they're constant. That's the important part. Mercury is not leaking a little, it's leaking continuously. And the contents of that leak are chemically interesting. Scientists didn't expect this kind of activity because they didn't think Mercury had anything left to lose. By this point in its life, the assumption was that its volatile inventory would be gone, stripped early, lost to the sun. But these atoms, sodium, potassium, lithium, calcium, say otherwise. They're still here. They're escaping into space, and they're being detected now. So when we say Mercury is emitting something weird right now, this is what we mean. It's not smoke or steam. It's not explosive gas or visible clouds. It's individual atoms, released one by one, forming faint tails and halos that shouldn't exist. They're proof that Mercury still holds onto materials we thought it lost a long time ago, and that it's still losing them, quietly but persistently, every single day. Starting with the most striking image, the sodium tail. This has been captured from Earth using telescopes equipped with narrowband filters tuned to sodium's specific wavelength. What you see in these images is a long, faint stream of light stretching away from Mercury. It's not a beam or a jet, it's more like a diffuse glow trailing behind the planet. That glow is what telescopes pick up, and it's consistent. It's not a one-time event. The tail appears every time Mercury is observed under the right conditions. Next is potassium. The potassium tail isn't as bright or obvious, but it's detectable. Researchers have used high-resolution spectrometers to measure the presence of potassium emissions trailing the planet. These are harder to image directly because potassium doesn't glow as strongly as sodium under solar UV. But the data shows a similar escape pattern. Potassium atoms pushed away from the planet by radiation pressure, forming a thin tail that moves with the solar wind. It's smaller, but it confirms that multiple elements are escaping the same way. Now look at Mercury's surface itself. The MESSENGER mission gave us high-resolution images of unusual depressions scattered across the surface. These are called hollows. They're not impact craters. They're shallow, irregular pits with bright halos and sharp edges. The edges aren't eroded, which suggests they're relatively young. They appear in clusters and are often found in places with high reflectance material. Scientists interpret these features as signs of volatile loss. In other words, something is escaping from beneath the surface, causing it to collapse slightly and leave behind these hollows. Even more striking, some hollows were seen to brighten and expand over just 4 years of MESSENGER observations, confirming that they are among the youngest and possibly still active geological features on Mercury. The images are clear. These aren't smooth depressions formed by flowing lava. They have a sharp, broken appearance, almost like bubbles that popped just under the crust. You can see where the material around the hollow is lighter, which supports the idea that sublimation or chemical erosion is removing darker material and leaving behind exposed rock. Some hollows appear inside impact craters, suggesting they formed after the impact, not during. In other words, this is a surface process still happening today. Recent global surveys using machine learning to analyze MESSENGER's full dataset have identified tens of thousands of hollows in various states of erosion, from bright, crisp, newly formed pits to older, faded remnants. Strong evidence that Mercury's surface is continuing to evolve. Then there's the thermal infrared imaging from BepiColombo. During flybys, its MERTIS instrument captured mid-infrared views of Mercury's surface. These aren't traditional photographs. They're thermal maps showing how different parts of the planet heat up and cool down. The infrared data reveals temperature variations across surface features, which helps scientists identify active regions. Some of the hottest areas are close to known emission zones. These temperature gradients may influence how and where particles escape. The MERTIS images show that Mercury's surface isn't thermally uniform. There are patterns, likely tied to both surface composition and structure, that could be connected to volatile release. None of these images is an artistic rendering. They're real data, taken from real instruments. The sodium tail seen from Earth. The potassium tail was captured in narrow spectra. The hollows observed close-up by Messenger. The thermal maps drawn from BepiColombo's flybys. Each one shows a part of the puzzle. Together, these images confirm what the numbers already told us. Mercury is losing material. Slowly, invisibly, atom by atom. But it's happening, and we can see the traces in light, in heat, and in the shape of the planet's surface. There's no need for guesswork when the visuals speak for themselves. Mercury's environment constantly strips atoms from the surface, and the mechanisms behind that are now fairly well understood. Each of them plays a role, depending on location, temperature, and exposure to space. The first is micrometeorite impact vaporization. Mercury is constantly bombarded by small particles of space dust. These particles are tiny, but they're moving extremely fast. Fast enough that when they strike the surface, they generate heat and shock waves that can vaporize surface material. This process breaks the bonds in minerals and releases individual atoms. If those atoms are light enough and have enough energy, they don't fall back down. They escape. Sodium and potassium are commonly released this way, and it's likely the lithium that's been detected is coming from the same kind of impact-triggered vaporization. Next is solar wind sputtering. The solar wind is a constant stream of charged particles emitted by the sun. When these particles hit Mercury's surface, they transfer energy to the atoms in the upper layers of the crust. That energy knocks some atoms loose. It's a slow erosion process, but it's always happening. And it targets the very topmost atomic layers, meaning the exosphere is fed directly by the top surface material. This is different from micrometeorite impacts, which are mechanical and thermal. Sputtering is more like a particle-level push. Another method is photon-stimulated desorption. This happens when ultraviolet light from the sun hits the surface and gives surface atoms enough energy to overcome the forces holding them in place. Some of those atoms gain just enough energy to escape Mercury's weak gravity. This works best for volatile elements, those that don't require much energy to release, which is why sodium and potassium are prominent. It's not explosive, it's more like gentle lifting, but over time it contributes significantly to the particle flow. Then there's thermal desorption. Mercury goes through massive temperature swings. These changes cause materials to expand and contract constantly. As the temperature rises, atoms near the surface can gain energy from the heat alone. If those atoms are loosely bound and lightweight, they can reach escape velocity. This mostly happens on the day side, especially in equatorial regions where sunlight is most intense. Over time, repeated cycles of heating and cooling also break apart surface minerals, exposing fresh material beneath. This slow churning of the upper soil layer is known as thermal gardening of the regolith, and it continually refreshes Mercury's surface. What makes all of this work is surface chemistry. Mercury's surface isn't just made of rock and iron. It includes volatile-bearing minerals, materials that contain sodium, potassium, sulfur, and now confirmed traces of lithium. These minerals don't need extreme conditions to break apart. That's why these escape mechanisms are so effective. The atoms are already near the surface, already weakly bound and already exposed. Mercury doesn't need internal activity or recent volcanism to release them. The environment does it for free, every second. It also helps that Mercury's gravity is low. Compared to Earth or even Mars, it's easier for atoms to escape once they've been released. There's no atmosphere to push back, no strong magnetic shield to trap particles in. Once an atom gets the energy it needs, it just leaves. That's why tails of sodium and potassium can stretch thousands of kilometers behind the planet. There's nothing stopping them once they're loose. These processes explain why Mercury is still actively leaking material, even though it hasn't been geologically active in billions of years. The escape isn't coming from below the surface, it's coming from constant exposure on the surface itself. Micrometeorites supply energy and crack open minerals. Solar wind strips atoms at the top. UV light lifts off volatiles. Heat loosens bonds, None of these is extreme by itself, but together, they're enough to explain everything we're seeing in the data. And because all of this depends on external input, not internal heat, it hasn't stopped. Mercury is still being hit, still being heated, still exposed. That means the emissions we're detecting now aren't remnants of an earlier era. They're ongoing, not in bursts or pulses, but in a constant, quiet release of material into space. Mercury is still shedding. And it's happening for reasons that are fully physical, measurable, and active right now. Scientists aren't looking at Mercury in a casual way anymore. Right now is a turning point because we have a spacecraft that has just completed its final gravity assist flyby and is now on the last leg of its journey to the planet, with instruments built specifically to measure what older missions missed. For years, most of what we knew about Mercury came from Messenger. That mission changed everything we thought we understood, but it also left a lot of unanswered questions. Now, BepiColombo, which has completed 6 Mercury flybys, is in the final stages of its cruise, and the timing lines up with new detections like lithium. Ironically, the same strange orbit that once made Mercury the perfect test for Einstein's general relativity is also what drives its modern particle loss. Because Mercury moves in a stretched-out orbit that brings it very close to the Sun, its path shifts slightly, 43 arcseconds per century, a result Einstein explained in 1915. But those same extreme conditions also expose Mercury to powerful solar forces that knock particles off its surface. These are exactly the effects BepiColombo is now equipped to measure. Mercury isn't just interesting again, it's clearly active, and that activity makes it a planet we need to watch closely. BepiColombo has instruments that were designed for this exact moment. Instead of broad-range surveys, it has sensors tuned to detect escaping atoms, track how they move, and measure their energy in real time. It can observe changes in the exosphere as they happen instead of relying on old data. It has a thermal mapper that can connect surface temperature patterns to particle loss. It has ion and neutral detectors that can pick up individual atoms and figure out where they came from. That kind of detail wasn't possible before. Messenger showed that Mercury was leaking material, but it couldn't track how the emissions changed over short time periods. It couldn't stay low enough or long enough to map chemical sources with fine detail. BepiColombo will. Once it enters orbit, it will be able to monitor the same regions repeatedly with higher sensitivity. That matters because scientists don't just want to know if Mercury is emitting particles. They want to know how strong the emissions are, how stable they are, and whether they change when solar activity increases. The discovery of lithium added urgency. It suggested that Mercury still contains materials no one expected it to hold. That means older models of how Mercury formed and evolved aren't complete. If lithium is escaping now, what else has been missed? And how much of it is being lost over time? This kind of detail could reshape planetary history, not just for Mercury, but for any rocky planet baked by a nearby star. There's also a bigger reason this moment matters. Mercury is the closest example we have of a rocky planet under extreme solar conditions. Exoplanet surveys keep finding small, hot planets orbiting very close to their stars. Some of them may be losing material in the same way Mercury is. Studying these emissions in our own solar system gives scientists a reference point. If we can measure how fast Mercury is losing sodium or lithium, we can estimate how fast similar planets are losing their atmospheres or surfaces. This is why scientists are paying attention now, not later. With BepiColombo closing in, they finally have the tools to answer questions that have been open for more than a decade. How does the exosphere behave hour by hour? Does particle escape increase during solar storms? Do certain areas release more material than others? Is the process accelerating or stable? These are specific, measurable questions, and for the first time, they can be answered. Mercury is no longer viewed as a dead world. It's a test case for how planets respond to extreme space environments. And the fact that it's emitting material right now, at the same time a new mission is arriving, makes this a rare opportunity. If the timing were different, we might have missed it. Instead, we're watching the planet in the one period where its behavior can finally be studied, not just detected. This is why the attention is close. Not because Mercury suddenly became more dramatic, but because the science finally caught up to what it's doing. Scientists have the instruments, the timing, and the data window all lined up. What happens next depends on what BepiColombo sees when it gets close enough to measure the leaks as they happen.